Okay, so it's a slightly different title to the one that was advertised. I've dropped the querying part and I've left the indexing part because I actually have a ton of content here. From a timing perspective, I could quite easily overrun a tiny bit, so I'm hoping to get through all of the content and give you guys some good feedback. This is a talk that actually was presented initially at MongoDB World in July. So we're delivering it here again because that presentation was so popular they needed to run it twice at World. So hopefully you guys will get as much out of it today. So before we move on, just a little bit about me. So my name is Ronan Bohan. I'm a principal solutions architect. That essentially means that I work with the commercial team. I'm a technical pre-sales engineer, more, for want of a better word. So I work with the commercial team and I help our customers understand the value and the benefit of MongoDB. I've been with the company for about 5 years. Started off in the support organization before moving into the commercial part, the sales part of the organization. With me today though, we're also going to have virtual Asya. You saw Asya a moment ago. She's actually delivering a presentation next door on the aggregation framework. Asya is one of our longest standing, most technically astute people in the company. She's currently a principal developer advocate. But she's going to be helping me a little bit today, and she's going to jump in every now and again with some interesting comments and questions around the talk. So she is going to jump in with things like this. She's going to essentially make a statement. In this case, she's identified some slow queries, and she wants to know what indexes she's going to create. And that's essentially the purpose of today's talk. In order to answer that question, we're going to talk about compound indexes in particular, and the ESR rule. An interesting kind of side, or an interesting aspect of MongoDB, and I guess any database in general, is that the performance of your database isn't the first thing you should look at when it comes to a MongoDB performance issue is not the hardware that the database is running on, but rather it is the schema design and the indexes that you're using to support the queries from your application. That's what we're going to focus on today. We're going to talk about this thing called the ESR rule. The ESR rule essentially is a guideline that we've come up with to help you guys get that best performance possible. It's something that's reasonably easy to understand, but it's something that trips up people over and over again. So this is not rocket science. It's classed as an advanced talk, but this is actually a pretty simple rule. If you keep reinforcing it, you'll get better at understanding the implications, and hopefully we'll be able to see some of that today. So, the roadmap for the talk, we're going to talk about the ESR. We're going to give an overview of ESR, and what is ESR? Those three acronyms, or those three letters. They stand for equality, sort, and range. So we're going to do a bit of a deep dive on each of those three components. I do want you to pay attention as well to the color coding. I've tried to make the presentation as understandable as possible, and everywhere you see green, it effectively means we're talking about equality, likewise blue for sort, and magenta for range. And that's going to carry through the presentation. Once we've finished our deep dive, we're going to look through some considerations. We're going to look at some operator type checks, and we're going to look at some exceptions to this rule that we're talking about. Okay, so without further ado, let's dig into this equality sort range rule and what that really means. Anybody who's used a database knows that the ordering of index keys in a compound index is going to be critical for your performance. Okay, so Asya jumps in immediately and says, yeah, but does that really matter? Well, let's have a quick look and example. So this is my little live demo, and hopefully it goes to plan. I have 2 clusters running on MongoDB Atlas, which I'll show you in a moment. But I'm just simply running 2 very simple queries. Or I'm running the same query, rather, against both clusters. I'm just simply running a very inefficient query on the 2 platforms. They have the same data, but they have different indexes. And one of the difference between the 2 clusters is that one is an M10. In other words, it's a reasonably low-powered machine, and the other cluster is an M30, so it's a more powerful machine. And I've color-coded them green and red here to kind of show you that actually what's happening in the background is that the M10 cluster, the top one, is running a lot more efficiently than the bottom one, which is a larger M30 cluster. And that's simply down to the indexes in place. So if I quickly show you those clusters, so up here on the top I have my M10. If I jump in here and look at my real-time metrics on both of these clusters, you should see in a moment, once it starts populating, I still have my network connection. Yeah, there we go. Okay. So this top window up here is for my M10 cluster. Oops. And we can see that we're getting about 73 operations a second at 3% CPU utilization. Whereas at the bottom, we see we're getting a lot lower queries in general, and we're using up 40% of the CPU. And this is down to the indexes that we've got created. Okay. If I quickly show you the indexes in place, you'll see that this machine has a compound index on what we're calling gamer tag and score, whereas this cluster down here has an index on score and gamer tag. So the same fields, just the reverse order. And that's the primary difference between these two clusters. And what I'm hopefully going to be able to do is, we'll return to this in a little bit later, but I'm going to create a new index. Hopefully I can just replace this content with what I have in my buffer. Let's click create, confirm that change. That's going to build that index, and we'll return to this in a little bit later, and we'll see the effect that it has. Okay. So this ESR rule that we're talking about provides guidance in most cases. And what it really means is that we should put our equality fields in our index first. We should follow that with our sort fields, and we should end with the range fields. So based on the queries we run in our application, we should structure our indexes in that order. Now, ASCII wants to know what's the difference between equality and range. So if people don't really know what equality, sort, and range are, hopefully you do, but let's go through a very quick definition. Equality fields first. So an equality field, as you're aware, is an exact match on an exact field. For example, x equals 1, 2, 3. Or maybe we'll use the $eq operator for the same thing. Or maybe we look at the value in a subdocument. In all three cases, the index bounds for that query is a type bound on the value 1, 2, 3, noted by the square brackets, so it's a single value range. Sort comes next, and it's when we talk about sorting in the context of the ESR rule, we talk about the entire requested sort. So if I were to sort on A1, for example, the sort there is the field, you're sorting on the field A in an ascending order. Whereas if I had a compound sort field, A ascending, B descending, we actually need to think about A and B in the order specified. A sort doesn't restrict the range of the query when it's run against it. So when we look at the index bounds, if we take the first example, sort on A, the index bounds for that sort component is going to span the entire range from the minimum possible value in MongoDB, min key, all the way up to the maximum value, max key. If we look at the more complex two-field sort, we actually end up with two sort fields, but both are in the span the entire range, min key to max key. Lastly, we talk about range predicates. Range is quite easy. It's essentially anything that doesn't match an equality. And some examples, greater than, look at the value of z greater than 9,000, or maybe look at the value foo less than or equal to 1,000. Again, first of those, the range when we look at those is anything above 9,000, noted by the round bracket. So saying that it's not 9,000, 9,000 is not part of the range, but anything above 9,000, all the way up to infinity and including infinity. And if we look at the foo example, we see that that is a range going from minus infinity up to and including 1,000. So again, using the sort of mathematical notation, square brackets and round brackets to determine exclusive or inclusive bound ranges. Okay. So that kind of sets us up. Let's talk a little bit about the first of those, equality. We said, as part of our rule, that the equality fields need to come first. It doesn't matter what order you specify them in, because the query planner will determine the query shape, and as long as the query fields are in specified first in your index, that index will be used for the, or is potentially used for the, to satisfy the query. So that's essentially the same thing. We need to form the prefix of the index should be the equality fields. Asia wants to know why that is. Well, let's have a look. Let's have an example. For the duration of, or for most of the talk, I'm going to talk about a set of sample documents, kind of orchestrated around a gaming system. And we're going to have these things called gamer tags, and we're going to have scores. And we saw a little bit of that in our live demo a few moments ago. And we're going to start off by looking at this example query. We're going to find documents where gamer tag is an equality field on the user ACE. And we're going to, just for the benefit of this first example, we're going to do a score greater than 9,000. So that's what I've said there. The real important thing is that we're focusing on this gamer tag, the equality field on gamer tag set to ACE. Let's move that to the top. Let's look at 4 sample documents in our example. We've got 2 users, Ace and Bob. User Ace has 2 scores, user Bob has another 2 scores. And we should be able to see from those 4 examples that this bottom left-hand document is the one that matches our query. We can see that straight away. So again, just for the benefit of the demo, let me move those documents, let's collapse them and move them down. And let's look at an index that we might build on top of those documents to satisfy this query. So I'm going to create an index based on score, followed by gamer tag. If you notice the ordering, we're talking about score, which is our range, followed by our equality, which is essentially an anti-pattern. This is not the way you should do it. But again, for the 3 components, what I'm going to do is I'm going to show you the anti-pattern, how that works, compared to then what the rule suggests and how that compares. If we build that index, we end up with essentially a 2-layer index structure in memory. We have score in the first instance, and we have gamer tag. We have score on the first layer, and we have gamer tag on the bottom layer. And if we look at our index bounds, we can see that to satisfy the query, gamer tag is actually on the second layer. So it's the second component of our index bounds, as we see on the left. And the score component actually is the first part of the index bounds, or the first part of the index bounds. Running through what the system actually does at that point, it starts off with the root node. The first thing it needs to do is the range scan on score. As we can see, we're looking for values that are above 9,000 up to infinity. So the very first document we need to search is this 15,000. We don't need to look at that left-hand column because it doesn't match the score predicate. Once we got the score, we jump down to the next layer, and we find underneath that we've got our gamer tag Bob. Bob doesn't match our equality, so that was a bit of useless work that we've just done. Move on to the second column, 50,000, but that also belongs to Bob. We're not interested in that. We then move to the last column in our index. As we've scanned across the index, the score value, we hit the value 99,999, and that does belong to Bob, or sorry, that does belong to Ace, which does match our query predicate, and therefore that's a document that we want to return to our users. So we've kind of done a lot of work to find one document. So let's get rid of that. Let's create a different index, this time following our rule. We're going to put equality first, followed by our range. This is our recommended index based on our rule. When we do that, the structure of our index changes. First of all, the gamer tag moves to the first layer, and there's only 2 values for gamer tag, Ace and Bob. And underneath those, we're going to put our score. Underneath that, the score, underneath each entry, the score will be ordered because the index has an ascending order. So that means we're going to have documents under Ace going from 100 up to 99,999. And likewise, Bob is 15,000 followed by 50,000. When we walk through, when we look at this example, we see the index bounds as before, but the order has changed, which matches the definition of the index. We've got gamer tag at the top. This is a tight bound on the value Ace. And underneath, we've got our range going from score above 9,000 up to infinity. Running through that, start at the root node, Because the first thing is an equality match, it means we can jump straight to the subtree where gamertag is ace. Underneath that, all we need to do is check one entry, because we are only looking for scores above a certain value, and there's only one of them there. At that point, we're done. We don't have to do any more work, because we know that the other values at that first layer won't match anything, because we've found that user ace. Comparing the before and after, on the left-hand side, you'll see what we did first when we used the anti-pattern. Right-hand side, we'll see the recommended pattern, and you should be able to see immediately that we've done a lot less work on the right-hand side in order to satisfy the same query, which translates into a more performant system. Okay, ASCII is reminding us that don't forget about our demo, so let's quickly jump back there. As you remember, we started off with 2 different indexes in the wrong order. We created a new index on our M30 cluster, and when we do that, if we go and look at our real-time metrics here, hopefully we'll see, switch back to real-time on both, real-time and real-time. Now you can see that this M30 cluster is down at the 3% level, and the operation count is that little bit higher. In fact, it's matching pretty much what we have on our M10 level. That basically tells us, just by changing the indexes that we've created, we're now running essentially our same workload on an oversized machine. And that gives us the opportunity to downsize our machine, our M30 to an M10, and potentially save money. This is a bit of a name drop. When I joined MongoDB, there was a support engineer who was very kind of adamant around looking at, from a performance perspective, looking at the schema design ahead of your production, your infrastructure. His name was William Zola. He's got a great video up on YouTube, so if you guys look up William Zola on YouTube and find that video, it's a 20, 30-minute talk, maybe made about 6 years ago, where he goes through this and he talks about why you should always look at your schema design ahead of any performance, infrastructure-related facts. By throwing money at the problem, just by buying more infrastructure, you're not really solving the underlying problem. Get your schema design right first, as we're showing here, and then the performance and the infrastructure size will fall naturally out of that. Okay. Okay. Next up. Okay, so we've talked about equality. Let's have a similar kind of deep dive into sorting. Okay, we said sort fields should come after your equality fields. By doing so, it allows your index to do certain things. It provides what we call a non-blocking sort, which I'm not going to go into right now. I'll talk a little bit later about. And it also minimizes the amount of scanning that's required. So let's look at this in a little bit of detail. Let's take the same 2 fields in our document, but let's do a different type of query. This time, we're going to do equality on gamertag, and then we're going to sort by the score. We're not going to use it as a range query, a predicate. Move that to the top. Let's create our anti-pattern index first. We're going to put our sort before our equality. We've seen that index before. We know the structure of that index. But one thing that's different here is because the score field is now a sort, if you look at the index bounds, we're going from min key to max key. Previously, we had a smaller, tighter range because we actually were looking for values greater than. In this example, we have to go from absolute minimum to absolute maximum. When we're looking at this example, these are the 2 documents that we want to return to the user, the left-hand side and the right-hand side. And we want to return them in a particular order based on the sorting that we're providing. In other words, we want to provide number 1 to the user first, followed by number 2. So let's run through that and see how it works. So we started our root node. We know that we're doing a range scan at this point across the entire range. So we have to start at the very left-hand side of our tree and go down to the child node there. We find that that matches, and we can return that document straight away. We can return that document straight away because we know that the very first thing we did was a range scan across the sort field. So that means that any documents we find in the order when we traverse through scores will return in the order we're looking for. So we can just simply return that out. Next up, we go to 15,000, but that belongs to Bob, not good enough. 50,000, Bob, not good enough. 99,000, well, that's ace. So that does match our query predicate, and now we can return that document out. And as you can see, we've found them in the correct order. Time to blow that one away. And let's look at the recommended index and compare that. If we create an index based on the equality field first, followed by the range, or followed by the score, which is the sort field, we get a different index. We get an index where Ace and Bob move up to the first level, and underneath those, we've seen this before, right? In this example, what we're looking for, again, are these two documents, numbers 1 and 2. And again, the index bounds here, we're going to start with an equality field on Ace, so a nice tight bound on that value. Underneath that, we're going to have a range over min key to max key. The nice thing here is that underneath each level in the first level of our index, all of the second entry fields are ordered with respect to the parent in the order specified by the index. When we run through this, we start at the top, we're doing an equality match. First thing we do is go down into the Ace subtree, and at that point, we can just iterate over all of the documents that we find, and in the order we find them, because they are created in that sequence based on the index definition. And we're done. So again, you can hopefully see when we follow our rule here, we've effectively done less work to achieve the same result. The other thing to bear in mind is that what we've done on the left-hand side, that index that we created actually triggered a full collection scan, or full index scan rather, over that first level field, right? We've actually had to go through every document on level 1 of our index and go down and check each value underneath it. So be careful about that, because, let's say, it may turn into a full index scan across your data. Next up, let's talk about range. Okay. Range fields are usually last in our index, based on our rule. This allows them to participate while filtering data, but it also doesn't trigger this thing called a blocking sort. Right? So now we'll talk a little bit about what that blocking sort is. You'll see an example. For this example, we're going to take gamertag and score. Gamertag is an equality field. Score is going to be a range. Move that to the top. Asir kind of correctly points out that we've seen this before, right? We don't even need to go through it. We know that the right-hand side is going to be better than the left-hand side. In other words, we need to put equalities before our range. But an interesting secondary question is, where does sort and range come? Does range come before or after sort? So let's change our query a little bit. We're going to change it such that we have an equality field followed by a range field on score greater than 9,000, and we're going to sort by gamertag. So effectively, we're going to do all three in this example. We don't have to worry too much about the equality field. Really, we're focusing on those last two fields. So I'll just collapse that down. For this example, we're going to go with the anti-pattern. We're going to put score first, score being the range. Range should not come before the sort field. So let's see what happens when we do that. Well, we know the index pattern. It's going to look a little bit like this. But for this example, I want to make things a little bit more interesting. So I'm going to take that third document and change Bob into Cal and see what effect that has. In this example, based on the query that we're running, we know we want to return these three documents that are circled. But because we have a sort, we need to return them in a particular order. And you'll notice that the order that they're listed in the index doesn't match the order that we want to get them back. From an index bounds perspective, we see again range over 9,000 to infinity, and gamertag is min key to max key. Let's start with our equality at the top. That's where we got to in our tree. Next thing we need to do is a range scan from anything above 9,000, so we can skip that first column, jump into the second. We find Bob. Bob, though, we can't return that to the user just yet, because there could be other documents which are earlier than Bob in the sequence. We can see it from the index, but the system doesn't know that yet. So it has to kind of put that document to the side and wait till the scan is complete before processing all the documents. 50,000 and cal, again another match, but we can't return that document either, so we need to put that somewhere else. And 99,000 and ace. At that point, we're finished. But these three documents need to be put into what's called a blocking sort stage. So blocking sort doesn't quite fit, so I'm going to create a BS bucket. And those three documents, once the scan is finished, all three documents essentially go into a new stage in the process, the blocking sort stage. That gets fully executed once the scan is complete. And its job is to output those documents in the correct order based on the sort request. So it outputs the documents in the order 1, 2, 3. At that point, we can deliver those straight back to the user. Okay. Let's look at the recommended index. This time we put gamertag before our score. So we have our sort field followed by our range field. Again, the index should be straightforward enough. We've got all those documents. My mistake. We blast away the previous version of the index, and we build a new index that looks a little bit like this. This is a bit different to before because now we have a new third field for gamertag called cal, so we have 3 entries on that level. And we can see underneath all of those that the values are, again, ordered in sequential order, but with respect to the parent node. Again, our index bounds are as expected. Walking through this example, the very first thing, once we got past the equality part, is to look into the gamertag. That's a range scan across the entire range. So we start off with ace. At that point, we're looking for scores above 9,000. So there's only one of those. We can find that document. And actually, we can return that straight away. I'll explain why in a moment. Bob, 15,000, also a valid entry that we can turn out to the user. And Cal with 50,000. And the reason we can output those documents in the order we find them is because those 3 documents, we got to them by going through the gamertag field in the order that matched the index. Okay, so what we've done here is we essentially, when it came to the index traversal, we've more or less done the same amount of work. But the nice thing about the right-hand side, when we follow the rule, is that we didn't have to introduce this additional blocking sort stage. And therefore, that will be a lot more efficient. That blocking sort stage effectively needs to make sure that the documents are stored more or less in memory before they're output to the user. So the more documents there are, the more memory you're going to use, and the more sorting you're going to have to do at the end. Okay, that's the bulk of the talk finished, but there are some interesting parts to come. First up, we have operator type checks. There's going to be a little bit of audience participation at this point in the presentation, so hopefully you're up for a little bit of Q&A from me. So we know some of the operators nice and simple. We've seen some of them already. Things like $EQ, that's an equality operator, nice and simple. GTE, for example, that's a range, we know that. Others tend to be a little bit trickier, and this is the bit that catches people out, right? So this is the bit that you can kind of constantly come back to this and relearn what you're going through. It's not that it's rocket science, but everybody kind of needs to think about this a little bit in order to understand the performance implications of what they're trying to achieve. So the first thing we're going to do is look at inequalities. So is an inequality operator an equality sort or a range field? As an example, not equal to 1, 2, 3. Anybody got any examples, or can anybody want to call out an answer? Any brave volunteers? Range. Somebody over there said range. Okay. What about not in 1 and 2? That's an inequality. Is that an equality sort or range? Okay. Well, it's a bit difficult maybe with the headset, so let's just run through that. You're correct, they are ranges. Asya, though, in her infinite wisdom, wants to know, how do we know that those are ranges? Well, let's have a look. If I focus on that first example, not equal to 1, 2, 3, when I look at the index bounds provided by the explain plan, we'll see that there are actually 2 entries related to that field X. To make it a little bit more concrete, let's look at a simple kind of index hierarchy, where we have the values 50, 1, 2, 3, and 999. the first row in that index bounds will target the left side of the tree, and the second row will target the right side of the tree. So in other words, altogether, we need to span two sides of a tree, and we need to look at all documents. Therefore, it's a range. Regex comes next. If I'm looking for the string car in a field called string, str, the question is that equality, sort, or range? These things aren't sort, right? So they're always going to be either equality or range. Make it a little bit simpler. Any ideas? Pardon? Range. Somebody else is saying range. Okay. What about if we change the regex to be a case insensitive with the /i at the end, and have it left anchored with the hat at the start? Is that also a range? Yes, no, heads, shaking? Well, again, they're both range, okay? Let's look at why they're ranges. Let's look at this little example with car, plane, and race car. That very first query, searching for car, is going to match, obviously, the document on the left, but it equally matches the document on the right, because we don't care where car appears in the word. But note that word in the middle, plane. We know it doesn't match, but the system doesn't, because it hasn't looked at it yet. Those three letters in the middle could be anything. So the system actually has to check that document to see if it matches the query. So in other words, we have to scan again the entire range. Focus on the second example, case insensitive and left anchored. Three documents, carry, rain, and zebra. Pretty simple, carry matches. It has car at the start. That last entry, zebra, though, what would happen if it was carpool with a capital C? Well, the thing is, that would match too. In other words, we're in the same position as previously. But here we go, Assia again. She wants to know, well, can't we just skip that middle document, because it is left anchored, and that document doesn't match, right? But that middle document could equally be carry with a capital A in the middle. That's still a valid sequence of entries with respect to the index. The point is, the system has to check every one of them. So it has to go through all of the work. It can't actually take any shortcuts. Okay, there you go. Car is embedded in there. And therefore, it's range. Okay, $in. This is probably the most tricky of the entries. Oops. I gave away the answer. $in. So for example, if I'm looking for my field, has a value of either 1 or 3. Well, I gave away the answer. The answer is it depends on whether it's treated as an equality or it's treated as a range. It really depends on how it's being used. If it's on its own, it's typically a series of equality matches. But if it's combined with other things, it can kind of turn into a range. I want to quickly run through this, and this is probably the trickiest part, and we have a couple of minutes left, so let's go through that. In this example, I'm going to create a compound index on field 1 and field 2, so a little bit different to before. And I want to try and figure out how that field 1 is being treated when I'm executing that find. Well, if I look at the index bounds on just that one find, I will see, very similar to what we saw before, we have 2 entries in our index bounds, type bound on the value 1, a type bound on the value 3. And really what that means is we're going to execute. Once we get past this thing that we're not necessarily sure about, we're going to jump into that left subtree and do an equality match on the value 1. And then we're going to find the 2 documents under that. Then we're going to switch over to the second field in our index bounds. We're going to target that right-hand subtree. We find the value 3, and it has 2 values A and D underneath it. So that effectively means that that top-level entry, when we execute a create index of this form, that field 1 is really being treated as almost a compound equality match. Now the thing is, what happens? Does it stay an equality kind of operation if we introduce a sort? Well, the first thing that really happens when we introduce a sort is we get a second field in our index bounds to match that second entry, and that targets that second row, third row in our index. we can see in the index that the values are sorted. C and G are sorted with respect to each other because they're under the value 1. And A and D are sorted with respect to each other because they're under the value 3. But we're asking for a range, a sort, that continues, or that's sorted across all 4 values. That effectively means that in order for us to take those 2 subtrees and sort them in a global sense, we need to put them into another blocking sort stage. So that pattern actually matches what we saw earlier with respect to our range queries. So that is, in effect, the same type of operation we get when we talk about ranges. There is a different way for the system to treat this kind of a query, and what it can do is it can treat them as 2 separate subtrees. So let's look at that. If I look at this at the left-hand side of the first value in the $in, I will get an index bound on field 1 that's tight on that value 1, followed by field 2 over the full range. Again, we go through that, and effectively that's an equality field followed by a range. We then do the second part of the operation, which triggers a parallel scan of the index, but this time where we're targeting the value 3 for field 1. In this case, we target the right-hand side of the tree, and we get the values A and D. Now, what we can see, of course, is that we are going to return those 4 values that are highlighted in blue, and we're going to return them, or we want them returned in the ascending order of the values that I've placed underneath them. In other words, we're going to return A first, followed by C, followed by D, followed by G. Now, how does the system do that? Well, what it's doing as it's going through these 2 things in parallel is that it's effectively, talk about that in a moment. On the left-hand side, it's gathering all those documents as it finds them. And likewise, in the right-hand parallel scan, it's finding the documents A and D, and it's going to gather those as well. And really what's going to happen at that point is that it's going to try and do a merge sort between those documents as they find them. And this is a little bit easier than it sounds, because if we focus on the left-hand side, that 2 and 4, they're already pre-sorted with respect to each other. We saw that from before. That means we only need to look at the very first document we found and kind of hold that in memory until we compare that to the right-hand side subtree traversal. And we only need to look at the first document we found there. And then we have to do just a very simple comparison between those 2 documents. Obviously, we can see 1 comes before 2, so that document A goes first. Whoops, let me go back. Once that document 1 is sorted, then we can find the next document, document 3. We compare 2 and 3, and we see 2 comes first, so A, or the value C, comes down. That allows us to move on to the next document in that left subtree, and we compare 3 and 4, and so on. So this is a very simple merge sort operation. It's a much more efficient sort than we looked at earlier, which is a blocking sort that happens after the entire process is complete. This happens while this traversal is happening, and it's a very simple comparison sort as opposed to a global sort. To put that in perspective, left side shows us the sort of all-in-one solution, but it requires a blocking sort, whereas the solution on the right-hand side is a dual traversal, and it has a merge sort in the middle, or as it's executing. Okay, we're coming towards the end. Last thing we need to talk about are some exceptions. Okay, so the question is the ESR rule always? I've told you that we've shown you examples, everything seemed to work out nicely, but is it always optimal? Well, short answer is nope. There are some cases where you may want to think about things a little bit more deeply. It's really a guide, not a rule. And we're going to look at a quick example here where we do 3 fields. We're going to issue a find with a sort. The find is going to have an equality on gamertag. It's going to have we're going to introduce a new field called date, where we're going to do a range scan, and we're going to sort by the score. If we take our recommended rule, we will create an index which has gamertag first, followed by score, followed by date. That creates the following type of index. Now, we've added in a new value here, which is the date field. In other words, when that person made that score in the game. We notice here on the right-hand side, we've got two scores from the year 2019. If we look at the range scan that we're looking for date that's equal to or above 2019. So really what we're going to be trying to target with this query is those two columns on the right-hand side, as we have here, documents 1 and 2. The index bounds, again, should be reasonably familiar at this point. The only real addition is that we've got this date field at the bottom, which has a tight bound from 2019 up to infinity. So let's run through what happens, start off in the quality on ACE. Next thing is the score across the entire range. So we have to start at the very lowest value, value 1. But that's from the year 2001, so that's not good enough. Let's look at the next column, 2, but that's from the year 2000. And so on, 5,000, 2015, until we get up to this value 9,000, which does match our query predicate. And the value 9001 was also created that same year. So that is also a value that we want to return out. Note, though, that we've had to traverse effectively the entire tree to get those two documents out. The net result in this particular example is that we haven't had necessarily to retrieve the documents, but we still have had to query essentially all of the keys in our tree. In this case, it meant traversing 9001 keys, only to return 2 to the user. So the question then becomes, is there a more efficient way to do this? And the answer is, well, yes. If we throw away our rule for a moment and make something that's a little bit more simple, just a two-value compound key with gamer tag and date, that changes the index, gets rid of that middle layer, it moves all the documents up one layer. The score is not part of the index now, so those scores are actually inside the documents. But we can treat that slightly differently. In this example, we only have 2 fields in our index, so our index bounds are tight bound on ACE, followed by a range scan on date. Walking through that, we find our ACE field. The very first thing that we do once we're in the ACE subtree is we find documents starting at 2019. And that means we can find that first document. We know that first document is a valid document. We now need to pull that document from disk, perhaps the full document, look at its score field. But now we see that that score field actually is 9001. We go on to the next document. It also matches. We look at its document. Its score is 9000. So the net result is that we found the 2 documents, but we found them in the wrong order. That means we need our blocking sort. So we take those 2 documents, put them into our blocking sort bucket, and the advantage here is that even though we have a blocking sort at the end, we're only sorting on 2 fields. And that also means that when we did the index traversal, we've only had to search 2 index fields to get those 2 documents. And although there is a blocking sort at the end, the amount of memory we needed to store those 2 documents is much smaller than the overhead of traversing that entire index in the past. We've saved a ton of index traversal steps. And this, in many ways, can be more efficient for your particular use case. So again, the example, it's kind of the counterexample is showing that, in certain circumstances, not following the rule might actually be more efficient. But in general, the rule is where you should start, look at whether that matches your query criteria, and then move on from there. So in summary, and we have, how many minutes left? We have 1 minute left. It's a good place to start. This ESR rule is a good place to start. Place keys in the order we specified, equality first, followed by sort, followed by range. But you do need to be a little bit pragmatic and careful. Remember, some operators may be range when you think that they may be equality. There are some subtleties around the different operators and how they're used that can throw you off a little bit. This is something I didn't quite get round to. I didn't have enough time to talk about in detail in this talk. It was there initially. But it is important that you have consecutive keys in your index as well. Okay, so I'm going to put these slides up afterwards, and there will be an appendix which kind of goes through this in a little bit more detail, so if you want to dig into that afterwards. But it is important that you put the index keys in your index in a consecutive order. And the last thing is that the rule isn't always necessarily the best thing. It does depend on your data, and it does depend on the kinds of things that you're doing with that data. It depends on your use case, effectively. And with that, I am done. There's the QR code if you want to rate the talk, which I would highly appreciate. I'll leave that up for a few minutes. We are just at 6 o'clock. The reception is taking place outside. I don't think we probably have time for questions right now, but I'm happy to wait around here for a few minutes if people have questions that they want to ask me.